In this video, we'll see what the determinant of a matrix is. We'll give a formal definition and some intuition as to what the determinant of a matrix really represents. So the way you should think about the determinant, the geometrical explanation or intuition for the determinant of a matrix is simply as the volume of some kind of a parallelepiped. So what is a parallelepiped? It's a generalization of a parallelogram to n dimensions. And so let's look at the two-dimensional case. So in 2 dimensions, what is a parallelogram? Parallelogram is basically quadrilateral where opposite sides are parallel to each other. And in 3 dimensions, a 3-dimensional parallelepiped is basically a polyhedron, basically the deformation of a cube such that opposite faces are parallel to each other, and this can be generalized to higher dimensions as well. So let's see a general mathematical representation of a parallelepiped in n dimensions, starting with the 2-dimensional case. So here I have a picture of a parallelogram in 2 dimensions, and really this can be described by the 2 vectors which correspond to 2 adjacent edges of the parallelepiped. So let's call this V1 and V2. Right? So we know that this side must be parallel to V1 and this side must be parallel to V2, and basically it doesn't take much effort to see that this parallelogram is basically the set of all points x in R2 such that x can be written as alpha 1 v1 plus alpha 2 v2 for all alpha 1 and alpha 2 which are between 0 and 1. Right? So clearly if you take v1 and v2, so if you take alpha 1 equal to alpha 2 equal to 1, then basically you get this diagonal vector which corresponds to this point over here. If you take any say alpha 1 v1 plus alpha 2 v2 for alpha 1 and alpha 2 being between 0 and 1, then you get in general a point in the interior of this parallelogram. Right? So this is how you define a parallelepiped in 2 dimensions, which is a parallelogram. And in general in n dimensions, a parallelepiped in n dimensions can be described by linearly independent vectors v1 v2 up to vn. So the parallelepiped defined by these vectors v1 v2 up to vn is basically the set of all vectors in Rn, which can be written as a linear combination of these n vectors, but not for all values of the coefficients. You only choose the coefficients to be between 0 and 1. Right? So basically in this lecture or in this and the next lecture, what I want to show is that the determinant of the matrix found by taking v1 v2 vn as the rows gives you the volume of this parallelepiped, or it gives you a means to find the volume of this parallelepiped. Right. So what is the volume of the parallelepiped equal to? So given the way that we've defined it, the volume of P is given by this formula. So it's the integral of the set of all x in P of dx. Right? And if you think about it, these v1, v2 up to vn are basically, they correspond to a transformation of a unit Q. So you can always think of a parallelogram as the transformation of a square, right? And where the transformation is described by the matrix given by v1, v2 as the columns. So if I take a matrix A which has v1, v2 up to vn as the columns, or it actually doesn't matter, I can also take them as the rows, right? Then the volume of the parallelepiped described by these n vectors is equal to the absolute value of the determinant of A. And the goal in this and the next lecture will be to show that this formula holds. Okay, but before that, we'll actually define I'll give you a very abstract definition of what a determinant is. So we'll define it to be any function which satisfies certain properties, and we'll see some properties about this of this definition of a determinant and what it has to do with the volume of a parallelogram or a parallelepiped, right? Okay. So in general, if I have an n by n matrix A, then the determinant, then I call it determinant function, basically a map from an n by n matrix to a real value. So D is what I call a determinant function, which takes a matrix and outputs a real number, right? So D is any function which satisfies these three properties. So these three properties are going to be properties of the rows of the matrix. In this lecture, we'll be treating vectors as row vectors instead of column vectors, because it will turn out that this is a more useful way to look at it. So the determinant function is any function of an n by n matrix which satisfies three properties. The first property is that the function D is what I call n linear. So in other words, if it is a linear function of the ith row, so for any I between 1 and n, D is a linear function of the ith row, provided that you keep all other rows fixed. So what do I mean by this? So let's assume that you have a matrix A which has rows v1, v2 up to vn, right? And let's suppose that we have another matrix B, which is basically the same as A. So all the rows of B are the same as A except for the ith row, right? So v1 so on up to, except the ith row, which is not vi but some vi prime, but the other rows are all the same as A, right? So both of them are n by n matrices, and they are identical except for the ith row. Then for any real number alpha, the determinant of or D, so D of v1 alpha vi one vn. So if I scale the ith row by alpha, then this is alpha times D of A. So you take any row, so for any general I, you take the ith row and scale it up by some factor alpha, then D of this new matrix is equal to alpha times D of the old matrix. Okay, and Also, you take two matrices A and B as I did earlier. So any two matrices A and B which differ only in the ith row, then D of A plus B is D of A plus D of B. Right? So this is the first property which my determinant should satisfy, and you should verify that even for the standard definition of the determinant that you have, this property is satisfied. So the standard notion of the determinant also satisfies this property that it is n linear. If you keep all the other rows fixed, then the determinant is a linear function of the ith row. Right? So for example, if I take A to be 1, 2, 3, 4, 5, 6, 7, 8, 9, then the determinant of A is equal to 2 times the determinant of this matrix 1, 2, 3, 2, 5 by 2, 3, 7, 8. Right? So these two matrices have the same. So determinant of A is 2 times determinant of this. Right? And also I can also write this as determinant of A is also equal to determinant of 1, 1, 1, 4, 5, 6, 7, 8, 9 plus determinant of 0, 1, 2, 4, 5, 6, 7, 8, 9. Check that this is indeed true. Okay, so that is property number 1. Right? The second property that any determinant function must satisfy is the following: that if you exchange any two rows of a matrix, then the determinant of the matrix exchanges sign. So for example, if I have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and I can exchange maybe the second and the third row to get 1, 2, 3, 7, 8, 9, 4, 5, 6. Then the determinant of the the matrix on the left hand side is equal to minus the determinant of the matrix on the right hand side. And also, if a matrix has two identical rows, then the determinant is equal to 0, and D of A is equal to 0. Right? And so that is the second property, which I call the alternating property of any determinant function. So here I'm defining a class of functions. So a determinant function is any function, any matrix function which has these properties, these three properties that I've listed here. Okay, in particular, the conventional definition of a determinant, the one that you've seen in your high school, is also a determinant function. Okay, and the third property is that the determinant of the identity matrix is equal to 1. And this is what the conventional definition of a determinant also satisfies. So these are three properties, and so any function which satisfies all these three properties is called a determinant function. and we'll see in this lecture and the next that a function which satisfies these three properties is unique, and it corresponds to our traditional definition of the determinant of a matrix. Okay. So the other point to note is that the conventional determinant satisfies all of these three properties, but even if I remove any one of these three properties, then the notion of a determinant function is not unique. So for example, if I have a function which is n linear and alternating, but determinant of I is not equal to 1, then it doesn't correspond to the traditional notion of a determinant. So for example, I could essentially define a function such that d of the identity matrix takes value equal to 2. So if I replace this definition with the property that d of the identity matrix is equal to 2, then I would get a different function, different from the conventional definition of a determinant, but the d function would still be consistent in the sense that there is no ambiguity as to what d is for a particular matrix. Okay, so for now we'll assume that a determinant function capital D, I call this capital D to distinguish from the traditional definition of a determinant, which I represent using det. Okay, so D is any function which satisfies these three properties of being n linear, alternating, and that d of I is equal to 1. Okay, so let's see what properties such a properties such a D function must have. So the first property is that if I take any matrix A which has the rows v1, v2 up to vn, and I scale the first row by some number a1, I scale the second row by a number a2, and so on. I scale each row by a number ai, then D of this new matrix, the scaled matrix, is the product of the AIs times D of the original matrix, consisting of the rows v1, v2 up to vn. So D of a1, v1, a2, v2 up to an, vn is the product a1, a2, a3, an times D of v1, v2 up to vn. And how do we get this? So I want you to pause the video for a minute and think about why and tell me why this property is true. Right. So the first property basically follows from the fact that D is n linear, right? So basically I have the D of a1, v1, a2, v2 up to an, vn is a1 times D of v1, a2, v2 up to an, vn, which is also equal to a1, a2 times D of v1, v2, a3, v3 up to an, vn, and so on. So it is basically an iterative application of the n linearity property of a matrix. Okay, so that's how you show property 1, and as a consequence of property 1, we have that D of any diagonal matrix is the product of the diagonal elements, right? And that follows from property 1 and the property that D of the identity matrix is equal to 1. Okay. So the third consequence of the definition of D is that if A has a 0 row, A could be any matrix, it need not be diagonal. If A has a 0 row, then D of A is equal to 0. So I want you to pause this video and think about why that is the case. Right. So if A has a 0 row, then you can always write, so let's suppose, without loss of generality, let's assume that the first row is 0. So A is 0 vector, from V2, V3 up to Vn. Now this can be written as 0 times any row V1, V2, but the other rows are kept the same, Vn, right? And therefore d of A would be equal to 0 times d of V1, V2 up to Vn, which is equal to 0 because 0 times any number is equal to 0. Okay, so those are three very easy properties. Now let's see something which is more useful, and these properties will be used in this and the coming lecture. So what happens if I do row operations on a particular matrix? How does the D function affect the matrix? Right? So clearly, just by property 2, that is the alternating property of D, if I exchange any two rows, then the sign gets interchanged. Right? So if I perform the elementary row operation of exchanging any two rows, then all it does is interchange the sign of D. Now, what if I do a basic row operation, which is I replace the ith row, I take Ri prime to be the ith row minus alpha times the jth row. Now, let's call the new matrix, let's call the original matrix A, and the new matrix A prime, which is V1 prime, V2 prime up to Vn prime. But what is that equal to? If A is V1, V2 up to Vn, then all other rows are identical except the ith row, which is Vi minus alpha times Vj, and the rest of them are the same, right? So basically this is an n linear combination of two matrices A and A prime. So recall, let's go back to the n linearity property. So suppose that you have a linear function. So the determinant is basically a linear function of the ith row when as long as all other rows are fixed, right? And here we're fixing all other rows. So if I have two matrices A, which is V1, V2 up to Vn, right? And B, which is the same as A except in the ith row. So here in the ith row you don't have Vi, but you have Vj, right? Vn. So since the ith row here is Vi minus alpha times Vj, we can consider two matrices where the ith row is Vi in A, which is basically the original matrix A, and another matrix B, which is identical to A except in the ith row, where instead of Vi we have Vj, right? So the determinant of A prime is basically a linear combination of the determinants of these two matrices A and B. So this is determinant of A minus alpha times determinant of B. But what is the determinant of B equal to? I want you to pause the video and think about this. Right. The determinant of B is equal to 0 because you have two rows which are identical. So this is equal to determinant of A. So this type of row operation, where you subtract a constant multiple of another row from a row, so this kind of row operation does not change the determinant of the matrix. Okay. Now we have a third row operation, which is the scaling of a row. So you can replace the ith row by a scaled version of the previous row, and we know that again from the n linearity property of the determinant of a prime is equal to alpha times the determinant of a. Okay. So this leads us to the following very important result. So if we have B to be the echelon form of A, so if we bring so if B is the echelon form of A, then what is D of B equal to? I want you to pause the video and think about this. Okay, so if B is the echelon form of A, then D of B is plus or minus D of A, depending on the number of row exchanges that you may have to do. And why is that the case? That is because to bring a matrix down to the echelon form, not the reduced row echelon form, just the row echelon form, you only need to do these two types of row operations. You may need to exchange certain rows, and you just need to subtract one row from a constant multiple of another row, right? And these properties do not change the absolute value of the determinant. The sign can only change, right? So if B is the echelon form of a matrix A, then D of B is plus or minus D of A, depending on the number of row exchanges required, right? And you can generalize this a bit. So in particular, if B is the echelon form with back substitution, so in other words, you take a matrix A and then you bring it down to the echelon form, so you get an upper triangular matrix. But then you can also do back substitution such that each column which has a pivot has exactly one non-zero entry. So it's not just below the pivot that you have zero entries, even above the pivot you have zero entry. So if you have this kind of an echelon form even with back substitution, then D of B is equal to plus or minus D of A, depending on the number of row exchanges required. So basically, in the echelon form with back substitution, the matrix B will be maybe of this form. Here's an example. So maybe 1, 2, 0, 0. 0, 0, 0, 0. This is one particular example, right? Okay. So this result is particularly important because we'll use this to prove the rest of the result. So basically, if B is the echelon form of A, then D of B is plus or minus D of A. Right? And that is because the first two types of elementary row operations do not change the absolute value of D. Okay, so let's see some important consequences of this. So suppose that we have a triangular matrix, then what is D equal to? I claim that D of a triangular matrix is equal to the product of the diagonal entries. And why is that the case? The reason is because if you have a triangular matrix, then the echelon form with back substitution is going to give you a diagonal matrix, and we know that the diagonal matrix, and the determinant or D of a diagonal matrix is equal to the product of the diagonal entries, right? So that is D for a triangular matrix. And if rank of, and what happens if the rank of A is less than n, then what is D of A equal to? For a square matrix, for an n by n matrix A, D of A is equal to 0, because the echelon form gives you 0 rows, so there is one diagonal entry which is equal to 0, and therefore D of A is equal to 0. So this property that D of a triangular matrix gives you the product of the diagonal entries of A, this implies that for any matrix A, you can very easily find the the determinant of the matrix just using row reduction, right? So the determinant is basically equal to the product of the pivot values. So D of A is simply equal to the product of pivots. Okay, so let's quickly see what happens for a general 2 by 2 matrix A, right? So let's do row reduction on the matrix A, right? So we'll be using this new definition of the determinant, right? So we'll do row reduction, and therefore the determinant is equal to the product of the pivots, right? So I'll do row reduction. I'll subtract the second row by a scaled multiple of the first row. So this is A11, A12, A21 minus A21 by A11 times A11. So my R2 prime is R2 minus A21 by A11 R1. So this is A22 minus A21 by A11 A12, right? So this is equal to A11 A12 0, A22 minus A21 A12 divided by A11, right? And so what is D of A equal to? So D of A is equal to the product of the diagonal entries, which is equal to A11 A22 minus A21 A12, which corresponds to our standard definition of the determinant, which is determinant det of A, right? Okay, so this is it for this particular video. So we've seen that in 2 dimensions, this new definition of the determinant, which is given just using these 3 properties, n linearity, alternating, and D of I equal to 1. So this corresponds to our conventional definition of determinant, at least for a 2 by 2 matrix. So in the next video, we'll see how this generalizes to n dimensions, and some more properties of the D function, and how this all relates to the volume of a parallel pipette.